Thank you, Tansel, for inviting me to give this talk. This talk is called Observer Design for Nonlinear Systems, a tutorial. And as the name implies, this lecture is a tutorial. It's aimed at introducing graduate students to the topic of nonlinear observer design. It's not intended to be a research seminar. So I'll start the tutorial by using a simple nonlinear plant for introducing the observer design problem. Then we look at Lyapunov analysis-based observer design and see how to set up the stability condition in the form of LMIs for designing the observer gain. Then we look at use of LMI solvers in MATLAB to solve the LMIs and find the observer gain. Subsequently, we'll look at more general nonlinear systems in which you have nonlinearities in both the process dynamics and the output equations, and there are also disturbances in the system. Finally, we will illustrate the nonlinear observer design by using an automotive slip angle estimation application. So we'll start with this simple plant dynamics. The system is x dot is equal to ax plus bu, where u is a known input, plus f of x. So f of x is the nonlinearity. Y is equal to cx. The output equation is linear. The observer is a replication of the system dynamics together with the output error feedback term. So x hat dot is ax hat plus bu plus f of x hat plus L times y minus cx hat. And we'll use the variable x tilde to denote estimation error. So x tilde is x minus x hat. So if you take the difference between equation 2 and equation 1, 1 minus 2 basically, then you get x tilde dot is a minus LC times x tilde plus f of x minus f of x hat. So if you had a linear system only without the nonlinearity, then your closed loop estimation error dynamics would have just been a minus LC times x tilde. So in this case, if AC is observable, then you can choose L to place the eigenvalues of A minus LC at any desired locations, and you can make the observer asymptotically stable. But now, because of the nonlinearity, you have this extra term here in the error dynamics, f of x minus f of x hat. And so we have to stabilize the observer in the presence of this term. Okay, so we have to stabilize the estimation error dynamics in the presence of fx minus f of x hat. We have to make some assumptions on the nonlinear function f of x. So typically f of x is assumed to be either Lipschitz or to have a bounded Jacobian, or it is assumed to be composed of monotonic functions. For the introductory part of this lecture, we'll start by assuming that the nonlinear function f of x is Lipschitz with a Lipschitz constant gamma. So f of x minus f of x hat, the 2 norm of that, is less than or equal to gamma. Gamma is called the Lipschitz constant, the 2 norm of x minus x hat. So that's the assumption on the nonlinear function. So how applicable is this Lipschitz assumption? For some Lipschitz functions, for some functions like trigonometric functions, sine x and cosine x, these are globally Lipschitz. So for example, sine of x or cosine of x, they are globally Lipschitz with the Lipschitz constant of 1. Many other nonlinear functions, they can be regarded as being Lipschitz. if the nonlinearity is differentiable and if the derivative is bounded. Basically, the Jacobian of the nonlinearity is bounded, it's got a lower bound and an upper bound, then you can assume the nonlinear function is Lipschitz. So furthermore, in many practical applications, the problem is not really with assuming that the nonlinearity is Lipschitz. The problem lies more with the size of the Lipschitz constant gamma. So sometimes you have to use a very big gamma to make the assumption that your nonlinear function is Lipschitz. And then if gamma is too big, then the observer design LMIs, they turn out to be not feasible. And so the challenge is, if you can either keep gamma small, or if you can find LMIs that are not very conservative, that can basically be more feasible for the given gamma. Okay, so we'll look at a couple of old results before we talk about LMI-based solutions. So again, the error dynamics, estimation error dynamics is x tilde dot equal to a minus LC x tilde plus f minus f hat. And so the obvious question that comes up initially is, if I choose the eigenvalues of a minus LC such that they are placed far into the left half plane, will that make the system stable? Will that overcome the presence of f of x minus f of x hat? And the answer is no, not necessarily. It's not just a function of the locations of eigenvalues of a minus LC. So one of the old results, this is a 20-year-old result from literature, is that basically it's not the eigenvalues of a minus LC, but the minimum singular values of a minus LC minus j omega I for all values of omega, that basically determines whether or not the closed loop system is stable. Here is yet another result from 20 years ago. So this result says that if the eigenvalues of a minus LC are chosen such that the real part of minus lambda for all the eigenvalues lambda, real part of minus lambda divided by the condition number of the eigenvector matrix, if that is bigger than the Lipschitz constant, then the observer is asymptotically stable. So this result basically says that the locations of the eigenvalues as well as the condition number of the eigenvectors, those are both important. So this ratio needs to be bigger than the Lipschitz constant in order to have the observer be asymptotically stable. So this slide basically just interprets what we just said. It's not enough to place the eigenvalues of a minus LC far into the left half plane. One has to also ensure that the eigenvector matrix is well conditioned. So observability by itself is not enough to ensure that a stable observer necessarily exists. The condition number of the matrix T, basically the eigenvector matrix, that depends on several factors, which include the locations of the eigenvalues, the distance to unobservability of the pair AC, and the condition number of C. So a number of factors play a role in determining whether or not the observer is stable. So based on these results, an old numerical procedure was developed. This was basically a gradient-based method in which the locations of the eigenvalues were continuously changed in the left half plane, so that the condition number of the eigenvector matrix was reduced. So it's basically a numerical procedure to keep reducing the condition number of the eigenvector matrix by changing the locations of the eigenvalues. And this was a method designed to converge to a local minimum of the condition number. But the problem with this method was that basically it depended highly on the initial eigenvalues chosen. So the eigenvalues that were chosen initially They basically determined what condition number and what eigenvalues you ended up with. And so it wasn't a very good numerical method. So this is, 20 plus years old. But in the last 20 years, there's been a lot of developments in LMI tools, and LMI tools have become very popular. So those can be used for getting more numerically viable solutions to the observer design problem. So let's look at Lyapunov analysis and how to use Lyapunov analysis to set up LMI constraints for the observer gain. So again, the estimation error dynamics is A minus LC x tilde plus f of x minus f of x hat. We start with the Lyapunov function candidate. So V is x tilde transpose P x tilde, and P needs to be symmetric, positive, definite. So we take derivatives of V along the x tilde dynamics given by 6. So V dot is x tilde dot transpose P x tilde plus x tilde transpose P x tilde dot, and then we substitute for x tilde from equation 6. So we Okay, so we substitute for x tilde dot from equation 6, and so V dot then turns out to be this quadratic term x tilde transpose A minus LC transpose P plus P A minus LC x tilde plus these sign indefinite terms. These are cross terms involving f tilde and x tilde. So f tilde is f of x minus f of x hat, so we'll call that as f tilde. So again, the first term is quadratic in x tilde, and so in this quadratic term we have A minus LC transpose P plus P A minus LC, which is what you would normally get for a linear system. And so if you would make that matrix negative definite, your observer would be asymptotically stable for a linear system. But now you have these sign indefinite cross terms involving f tilde and x tilde. So we use the Lipschitz assumption on f tilde. So the norm of f tilde is less than or equal to gamma times the norm of x tilde. So we can substitute that in the Lyapunov function derivative. So V dot, we have the first quadratic term that remains the same, and then f tilde gets replaced by equation 7. So you get gamma times x tilde transpose and then norm of P x tilde, norm of x tilde transpose P gamma x tilde. So you can see that these two terms here, they essentially involve the same two quantities, A and B. And so you can use this very simple algebraic trick. 2AB is less than or equal to A square plus B square. So these terms are, they are both A times B terms. And so using the simple algebraic identity with A equal to gamma times norm of x tilde transpose and B equal to norm of x tilde transpose P, you end up with this V dot. V dot is now all the terms in V dot are quadratic. So you have A minus LC transpose P plus P A minus LC, and then this is another quadratic term in x tilde with gamma square I, and this is one more term, quadratic term in x tilde with P times P. And so your Lyapunov candidate derivative is V dot less than or equal to this quadratic term with this matrix here, A minus LC transpose P plus P A minus LC plus gamma square I plus PP. And so the conditions for stability are that this inequality needs to be satisfied. A minus LC transpose P plus P A minus LC plus gamma square I plus PP needs to be less than 0, and P needs to be a symmetric positive definite matrix. That would give you V greater than 0, V dot less than 0, and you'd get a stable observer. So the question is, how do you find L and P to satisfy these equations here, these two equations? So what we do is we use an LMI solver in MATLAB to solve these equations and find L. So you can find a lot of introductory material on LMIs on the web if you do a quick search. But basically, solving an LMI involves solving this equation, an equation of this form. F of x is f0 plus x1 f1 plus x2 f2 plus x3 f3 and so on is less than or equal to 0. So this is a linear matrix inequality. The x's, the x1, x2 and so on, those are the decision variables. Those are the variables that we need to find. And the fi's, f0, f1, f2 and so on, those are known matrices. They're known symmetric matrices. So for example, they could be the basis matrices for all symmetric matrices of size n by n, for example. So so an LMI constraint is basically a convex constraint, and so there are good numerical tools available for solving these types of basically objective functions that are constrained by these types of LMIs. So for example, P greater than 0, that is an LMI. A transpose P plus P less than 0 is an LMI. And so from linear systems, we know that if we can find a P that satisfies both of these equations, P greater than 0 and A transpose P plus PA less than 0, then we would be verifying that A is asymptotically stable. So there's a toolbox called YALMIP that can be downloaded and used inside MATLAB to solve LMIs. So this toolbox is available for free on the web. It doesn't come with MATLAB, but you need to download it and install it. And they have really good help tools and tutorials that tell you how to download and install, and how to install additional numerical solvers, as well as how to actually use the programs for calling the YALMIP solvers. So on the following slides, I'll show you a program for solving a LMI problem similar to what I just showed you. Okay, so we'll use this illustrative example. This is just a linear time invariant, so it's basically a linear time invariant system observer. Again, what we'll do is we'll just use the simple example to look at some code for solving LMIs. So the plant is x dot is equal to ax plus bu. The output is y is equal to cx. So the observer equation, again, like before, we replicate the plant dynamics, and we have linear estimation, linear output error feedback. Estimation error dynamics are given by x tilde dot is a minus LC x tilde. So our objective is to find positive definite matrix P such that A minus LC transpose P plus PA minus LC is less than 0. So if you expand out A minus LC transpose P plus PA minus LC less than 0, that is basically A transpose P plus PA minus C transpose L transpose P minus PLC less than 0. And so straight away you can see that this is not really an LMI. This is a BMI or a bilinear matrix inequality, because it involves a product of L and P. So there are two variables that we are trying to solve for here. The two variables are P and L, and so a product of P and L is involved in these two terms. And so this is not really an LMI, but it can be easily converted to an LMI. what you need to do is you need to define a new matrix R, which is equal to P times L. So R is equal to P times L. So when you substitute this in this equation, in the star equation, you get A transpose P plus PA minus C transpose R transpose minus RC less than 0. Now this is an LMI if you treat P and R as being completely independent variables. So P and R are completely independent, so this is a linear matrix inequality, and you can solve this using the LMI solvers. Once you solve this inequality and you find R, because R is equal to P times L, you can find L using P inverse R. Because P is required to be positive definite, P inverse exists, and so therefore once you find P and R, you can find L, and so this is a viable method for solving the observer design problem in this case. So this is example MATLAB code to solve the LTI system observer LMI. So this MATLAB code is really easy to follow. What we're doing in the beginning is we're defining the A and the C matrices. So this is a third order system. So A is kind of a kinematic motion model, and you can see that it's not stable by itself. It's not asymptotically stable. P and R are the two matrix decision variables. These are the ones that we need to obtain by solving the LMI. This is how the LMI constraints are set up. So it's A transpose P plus PA minus C transpose R transpose minus RC, and this is exactly what we had on the previous slide, and this is how we set it up. This is the syntax for setting up the LMIs for the solver. This is the part of the file that chooses which solver you're going to use, which LMI solver. So for example, LMI Lab is one of the solvers that is available inside MATLAB. Sedumi is an external solver that you can download. This is the code that basically calls the LMI solver and finds the solutions. This is where you're checking for the results of the LMI optimization. So you know, if the diagnostics problem is 0, if your LMI is feasible, if you're able to find a solution to the LMI, you'll get a diagnostics.problem equal to 0. And once you do that, then you have all the matrices you need. So basically P and R are returned by the solver, and you find L by using P inverse times R. So this is really easy, and for this particular problem, the A and the C defined here, you know, the system will be solvable, and you'll find that you can solve it. Okay, so let's go back to the nonlinear observer design problem. Okay, so in the case of the nonlinear observer design problem, this was our LMI. I mean, this was our inequality that we needed to solve. A minus LC transpose P plus PA minus LC plus gamma square I plus PP less than 0. And you know, you certainly need to use the same trick that we used earlier. We need to define the matrix R is equal to PL. So when you substitute R is equal to PL, this is what the inequality becomes. You get A transpose P plus PA minus C transpose R minus RC plus gamma square I plus PP less than 0. Okay, so now you need to solve for P and R. But again, you have this quadratic term, P times P. So this is not an LMI yet. This is also known as an algebraic Riccati inequality. So you need to convert this to an LMI, so you need one more step, and what you can do is you can use the Schur complement lemma to convert this quadratic inequality to an LMI. So the Schur complement lemma is as follows. So this LMI, QS transpose R, so this is obviously a symmetric matrix. Q is assumed to be symmetric, R is assumed to be symmetric. So this LMI, this is a linear matrix inequality, is equivalent to this quadratic inequality. The quadratic inequality is that R is less than 0 and Q minus S R inverse S transpose, this is less than 0. So, so this is the quadratic inequality, right? And this is just a linear inequality. So this LMI is equivalent to these two equations. So you can basically convert a quadratic inequality to an LMI by using the Schur complement lemma. So that's what we have done here on this slide. We have this quadratic inequality, algebraic inequality involving P transpose P. And so by defining R is equal to minus I and S is equal to P, and using the Schur complement lemma, we end up with this LMI. Okay, so this LMI is basically A transpose P plus PA minus C transpose R minus RC plus gamma square I. So this is the 1-1 term. This is basically a, you know, a 2n by 2n matrix. So this is the LMI that needs to be solved. And along with this, you also have P greater than 0. Okay, so this, you know, this can be solved using the same code that I just showed you. So this can be put into, you know, you can redefine your matrices and you can use the same code and you can solve LMI. So that's how you would do observer design for the specific nonlinear system that we considered. Okay, so that design would give you the P and the L matrix, and so with that L, your observer would be asymptotically stable. Okay, so one of the simple tools that you can use to make the likelihood of a solution existing to the LMI more feasible is to use a matrix Lipschitz constant instead of a scalar Lipschitz constant. So sometimes basically you might find that your observer design LMI is not feasible because gamma is too big. So what you can do is you can replace this constraint on f of x with a scalar Lipschitz constant with this matrix Lipschitz constant. So norm of f of x minus f of x hat is less than or equal to, and then inside the norm you have g times x minus x hat. So this is a matrix Lipschitz constant g, and using a matrix Lipschitz constant is less conservative because G can be a sparse matrix if the nonlinear function only involves a few states. So for example, let's say your nonlinear function was this, let's say your f of x was 2 sine x1 0. So if we use the traditional scalar Lipschitz bound, in this case you would essentially get this constraint being satisfied. So the scalar Lipschitz constant is 2. Okay. On the other hand, if you use the matrix Lipschitz bound, this is the constraint that would be satisfied. Okay. So the matrix Lipschitz constant is basically 2 0 0 0, and so basically you can see that this matrix is sparsely populated. Most of the elements in it are 0, and your LMI changes. So instead of gamma square I, the gamma square I term is replaced by G transpose G in the observer design LMI. Okay. So this is your new LMI for making the observer stable. So this can be supplied to the LMI solver in MATLAB. Now G transpose D is likely to be less than gamma square I, because G is a sparsely populated matrix. So G transpose G is going to be less than gamma square I. So this LMI is likely to be more feasible than the original gamma square I LMI. So this is one of the simple tricks you can use to try and make your LMIs more feasible. Okay. So then let's look at a different type of constraint on the nonlinear vector F, nonlinear function F. So let's assume that, so earlier we basically assumed that the nonlinear function F was Lipschitz. Now let's look at the nonlinear function having bounded derivatives. So basically the Jacobian dou F by dou X has lower and upper bounds. So K1 is less than or equal to dou F by dou X less than or equal to K2. So this operator here is an element-wise inequality operator. Okay. What that means is basically if you look at dou Fi by dou Xj, okay, then K1 of I comma j is going to be less than or equal to this, and K2 of I comma j is going to be greater than or equal to this. Yeah. So for example, if I have a second order system, so F is equal to F1 of x1 x2 and F2 of x1 x2, then the derivative, the Jacobian, is basically dou F by dou X. The Jacobian is this: dou F1 by dou X1, dou F1 by dou X2, dou F2 by dou X1, dou F2 by dou X2. So each of these functions is bounded by K1 I comma j and K2 I comma j. Yeah. So each of these functions has an upper and a lower bound, and this is the element-wise inequality that is being satisfied here. Okay. So how do we use these Jacobian bounds to set up the observer design LMI? So it turns out that first of all, let's define f tilde as f of x minus f of x hat. So this is the same as before. If we use the differential mean value theorem, we can show that if K1 and K2 are the bounds on the Jacobian, then we can show that this inequality is true. Okay. So what is this inequality? F tilde minus K1 x tilde transpose f tilde minus K2 x tilde less than or equal to 0. Okay. So because of the bounds on the Jacobian, this inequality is true. Okay. So this is a row vector, this is a column vector, so this is basically a scalar. So this is easy to understand in the case of scalar functions. You can see that if f was a scalar function, then f tilde is basically larger than K1 x tilde, so this is positive, and f tilde is less than K2 x tilde, so this is negative, and so this inequality is true. So that's easy to see in the case of scalar functions. It turns out that this inequality is true for not just scalar functions, for basically any vector function f of x. So this is true for all vector functions, and you can see the proof of this in some papers that I can send to you. So this inequality, you can represent it in matrix form as follows. Okay, so you know, this basically involves quadratic in f tilde, quadratic in x tilde, and cross terms involving both f tilde and x tilde. And so therefore, in matrix form, you can represent it as follows. So if your vector has both x tilde and f tilde in it, and it turns out that this is going to be true even if you swap K1 and K2, and so a symmetric form of this inequality, is equation 17. Okay. Okay. So what we've done is we have found a way to represent bounds on the Jacobian of F. Okay. So we found a way, we found an inequality to represent the constraint due to the Jacobian bounds. And so by using this constraint on F, we can come up with a LMI result for observer design for making the observer asymptotically stable, and this is the result. This is the observer design LMI. So if you look at this design condition, so here you can see you have A minus LC transpose P plus PA minus LC, and then you have P and P on the off diagonal terms, 0 over here, minus you have this term. This is the term that came from the constraint on the Jacobian of F. Okay, so this is less than 0. So K1 and K2 are the bounds on the Jacobian. Those are fully known, right? Those are known to you because the nonlinearity has a bounded Jacobian. So these terms are all known. What we need to do is solve for P and L, and so you can solve for P and L. You can again define P times L as a new matrix R, and so exactly using the same procedure as before, you can use the LMI solvers in MATLAB to find L and P. And this result can be proved by using the S procedure lemma. So I have an outline of the proof here on the next slide. Basically, it turns out that V dot, the derivative of the Lyapunov function candidate, is given with this quadratic involving the vector x tilde f tilde, and then this is the inequality again involving x tilde f tilde that comes from the Jacobian bounds. And so by using the S procedure lemma, where V dot is going to be less than 0 if and only if V dot is less than epsilon times V0, and by absorbing this epsilon into the P matrix, we can essentially show that the previous equation, this is the previous equation, this is the observer design equation, we can show that this equation is true. And so this proof you can find in our paper published a few years ago. Okay, so that is a easy observer design LMI that you might find to be very useful for your applications. Okay, so given a nonlinear function in general, you'll be able to see if your nonlinear function is differentiable. You'll be able to find bounds on your Jacobian, and then you'll be able to essentially find the observer gain that stabilizes the system. Now you can also add performance constraints to the observer design. So for example, if you want to add convergence rate to the observer. So basically, if you want to have x tilde converge with a convergence rate of at least sigma by 2, the exponential convergence of at least sigma by 2, then the observer design LMI gets modified just a little bit. This term plus sigma p gets added to this matrix here. Okay, so the LMI changes just a little bit. You can add a convergence rate constraint by modifying the LMI with this term. Next, if you have a disturbance W, so if your plant is given by x dot is equal to ax plus b times W plus f of x, so W is basically you have a disturbance here now instead of a known input. Okay, and your output equation is still linear, then you can add a H infinity disturbance rejection constraint in which basically the ratio between the 2 norm of x tilde to the 2 norm of W is the disturbance, so that is basically bigger. So this ratio is less than mu. So this H infinity disturbance rejection constraint can also be incorporated into the observer design LMI. And so the new LMI that incorporates this H infinity disturbance rejection constraint is given by equation 20 shown here. So what you'll see here is that, because of the B times W term that you had in the plant, you get these extra terms here, PB and B transpose P, these off-diagonal terms, and you get this minus mu I term, which is the 3 entry here in this matrix. The second matrix doesn't, basically the top part of that doesn't change. You have zeros added over here. Okay, so this is a new observer design LMI. And so what does this LMI do? It gives you a minimum convergence rate by having this plus sigma p term here. It also gives you an H infinity disturbance rejection constraint being satisfied, and so that comes from this minus mu I term and these PB terms that are in the LMI. So again, this is an LMI that you can supply to MATLAB, and MATLAB will find an observer gain L for you, and your observer will be exponentially stable. It will satisfy an exponential convergence rate of sigma by 2, and it will satisfy an H infinity disturbance rejection constraint. Okay. So finally, let's just talk about a more general nonlinear system and just present the result for that. So we basically extend the previous result to systems with nonlinear output equations. So this is a plant. X dot is equal to AX plus BF times F of X, plus this is a term that involves only the output and known inputs. So this term is essentially completely known. And then this is the term involving the unknown disturbance W. And your output equation is no longer linear. It's not Cx, it's H of X. So we make assumptions on the two nonlinear functions, the two nonlinear functions being F of X, which is the nonlinearity in the process dynamics, and H of X, which is the nonlinearity in the output equation. So dou F by dou X, this Jacobian has lower and upper bounds, and dou H by dou X has lower and upper bounds, which is, these are again element by element inequalities here in equation 22. It turns out that you can rewrite the system equations by defining new functions f bar and h bar. F bar is f of x minus kf1 times x, and h bar is h of x minus kh1x. So basically the lower Jacobian bound is being used in both these cases. So the reason why we rewrite the system equations in this way is because it makes the derivations easier, especially if you want to have more observer degrees of freedom. So if you want to have, in addition to the observer gain matrix L, if you want to have additional gain matrices, observer gain matrices that are injected through the nonlinear functions f and h, basically you can have more observer degrees of freedom by having these additional observer gains. Then it turns out that by making these defining these new nonlinear functions, your derivations become easier. So I won't go through the algebra too much, but I'll just show you the final result. So there is the Jacobian conditions. Again, you have very similar conditions to LMIs being satisfied due to the Jacobian bounds. These are similar to what I showed you for the earlier simpler case. And the observer design result is that the observer is asymptotically stable and satisfies the following H infinity disturbance rejection constraint involving mu. So mu is the H infinity gain between the estimation error and the disturbance. So if you can find a positive definite matrix P and an L that satisfy the LMI on the following page, then this observer is stable. And this is the observer design LMI. Okay. So this LMI involves these known bounds on the Jacobian, KF1, KF2, KH1, KH2, A bar, BF, these are known matrices. We need to solve for P and L. Mu is the H infinity gain. Tau is a scalar constant that needs to be positive. So it's allowed to be any positive scalar constant. So you can solve this LMI in MATLAB, and that gives you a stable observer with H infinity disturbance rejection constraint as well. Okay. So then I come to the final part of my talk. I just want to show you an example of how a nonlinear observer can be used for an automotive slip angle estimation application. So first of all, what is slip angle? Slip angle is basically the angle between an object and its velocity vector. Okay, so for example, the slip angle of this car is the angle beta between the velocity vector at the CG of the car and the orientation of the car. That's the slip angle of the car. You can also define slip angles at each tire, and again the slip angle at the tire is basically the angle alpha between the velocity vector at the tire and the orientation of the tire. Okay, so essentially slip angle is the angle between an object and its velocity vector. So where is slip angle useful? Why would you want to estimate slip angle? One of the applications in which slip angle is useful is electronic stability control. So electronic stability control is also known as, sometimes known as yaw stability control. So what is done in electronic stability control is differential braking. So different amounts of braking are applied to the left and the right tires. So that the yaw rate or the turn rate of the car can be controlled in order to prevent the car from skidding. So this illustrative schematic that is shown here on the slide tells you how an electronic stability control system might work. So here what you see is on a high mu road, basically on a dry pavement, the car would essentially follow this trajectory. So for a given steering angle, right, it would follow this trajectory. You can see that the orientation of the car is essentially aligned with the orientation of the road. On the other hand, if the road is slippery, if the road happens to be icy, has a low friction coefficient, then the car can skid. And so two things can happen. First of all, instead of going on the trajectory that you expected to go on, the car is going to go on this trajectory of a different curvature. So basically you might have a lane departure because of the slippery road. Okay, so you're not able to go on as tight a curve as you were able to go earlier with the same steering angle. Okay, your car goes on a trajectory with a lower curvature. Not only that, but your car can get misaligned with respect to the road. So what you're seeing here is that the car is oriented in a direction which is not the same as the direction of the road. So the car is actually oriented this way, but the velocity of the car is along this trajectory. This is the trajectory of the car. So because this is the trajectory of the car, the velocity is along this direction, but the car is along that direction. So there is basically a big slip angle between the orientation of the car and the orientation of its velocity vector. So this is obviously something that you would like to avoid. You don't want to have a lot of lateral velocity. You don't want to have a big slip angle because that basically means you're skidding on the road. So, so this is an example of where you would like to control not only the yaw rate of the vehicle, but you'd also like to control the slip angle. You'd like to keep the slip angle small so that you don't get much skidding. Slip angle is also important in many other automotive safety systems. So this is one of them, electronic stability control, also useful in some other systems as well. Now it's not really possible to measure slip angle, especially to measure it well. So some sensors that are available to measure slip angle, for example, optical sensors. These optical sensors basically look at the texture of the road and they find the velocity vector by doing that. They are very expensive. For example, the cost of the Corsa's data on an optical sensor could be as much as $10,000 or higher. Therefore, it's good to estimate slip angle rather than try to measure it, because the sensors for measuring it are too expensive. Okay, so how do we estimate slip angle? We basically use a model of the car which involves the lateral degrees of freedom. So the lateral degrees of freedom are basically the lateral translation of the car. So the X is called the longitudinal axis. That's basically the axis of primary motion of the car. So Y is perpendicular to that. It's the lateral axis. And so the 2 degrees of freedom are the lateral translation and the rotation side out, the yaw rate side out. Okay, so these are the 2 degrees of freedom involved in, and so typically you get you know, either second order or fourth order equations depending on whether you're only considering velocities or also positions. Now, the tire force models are nonlinear because in electronic stability control is basically useful when the road is slippery. So it really needs to consider nonlinear tire force models. It cannot really use linear tire force models. So this is an example of a nonlinear tire force model that could be used. Okay, so the lateral force is a nonlinear function of the slip angle at the tire. Okay, so you can define the slip angles at the tires, the slip angles at the front tire and the slip angles at the rear tire in terms of psi dot and beta, where beta is the slip angle of the vehicle and delta is the steering angle. So it turns out that the model equations for this system can be formulated to be entirely in terms of front and rear tire slip angles. Okay, so also the outputs. So we look at the model equations on the next slide. The outputs for this system, the measurements, are yaw rate and lateral acceleration. So these are outputs that are easily available. They are inexpensive. So yaw rate, you can measure yaw rate using a gyroscope. So that's an inexpensive sensor. You can measure lateral acceleration using an accelerometer. So that's again an inexpensive sensor. So this is a very inexpensive set of sensors. And so if you can estimate slip angle by using these together with measuring steering angle, then you have a good system for estimating slip angle. So these are the model equations for the slip angle estimation system. So the state variables are the slip angles at the front tire and the slip angle at the rear tire. So d by dt of alpha f and alpha r. So these are the states. And you can see that the system dynamics are nonlinear. You have a linear portion. So you have a times x. So you have a linear portion. Then you have the known inputs, the terms involving the known inputs. Okay, so this is delta, delta dot, and the lateral acceleration. And then you have the nonlinear term. So this is the nonlinear function f of x. Okay, so why is this nonlinear? Because it involves eta of alpha f, and eta is this nonlinear function. So this basically comes from the nonlinear tire force model. Okay, so these process dynamics are like the dynamics that we considered when we looked at the theoretical results on observer design. So basically there is a linear portion, there is a known term, known input term, and then there is a nonlinear term here. And so x dot is ax plus bu plus f of x. And if you look at the output equation, so the outputs are basically the yaw rate and the lateral acceleration. And so if you look at the output equation, You have a linear term again, c times x. Okay, so this is a linear term. And then you have a nonlinear term as well, h of x. Okay, so y is cx plus h of x. Okay, so so the slip angle estimation problem can be set up using the same theory that we discussed earlier. So we found the observer gain for the slip angle estimation problem, and then we evaluated it by using tests on a Volvo XC90 SUV vehicle. So we did tests on various types of pavements, including slippery pavements with this vehicle. And so this is an example of some data being shown to you here on the right hand side. So what this figure has is essentially lateral acceleration, so that's proportional to lateral force, and slip angle on the x-axis. And if the force had been a linear function of slip angle, then basically you would have seen a linear relationship here. Force would have increased linearly with slip angle. But what you can clearly see here is that there is saturation happening. There is a nonlinear relationship between force and slip angle. So clearly this is a nonlinear system, and you need to use nonlinear dynamic models in order to be able to do slip angle estimation for this application. We used an expensive RT3000 expensive IMU combined with the GPS system in order to find reference slip angles with which our own slip angle estimates could be compared. And so these are some experimental results that are shown in the next couple of slides. The first result that you see here on the left hand side is basically a double lane change maneuver on a dry road, basically regular asphalt pavement, 70 miles per hour driving, and a double lane change is being done. And slip angle is estimated by us by using an inexpensive accelerometer and an inexpensive gyroscope. And so these are, so our estimates are shown in black, and in blue are the reference slip angle, and you can see that our estimates match quite well with the reference values. On the right hand side, a different kind of random driving maneuver on a dirt surface. So this is basically a dirt road, not a paved road. So the friction coefficient is unknown. The friction coefficient was not necessarily low here, but it was just unknown. It wasn't a paved road, and we were still able to do a pretty good slip angle estimation on this surface. Now this is a test run on a slippery surface, basically a double lane change maneuver with on an icy road, low friction road surface. And what we did here is we assumed that the friction coefficient was known, and by doing that we were able to estimate slip angle quite well. It turns out that friction coefficient can be estimated by using other methods, basically methods based on longitudinal dynamics. You can estimate the friction coefficient, and then you can use the lateral dynamics to estimate the slip angle. And so you can see that the slip angle is estimated reasonably well on this surface. So to conclude, in this tutorial, we talked about use of Lyapunov analysis, use of the S procedure lemma, and other tools for obtaining LMI-based observer design solutions. Essentially, we need to solve LMIs to find stabilizing observer gains, and we can find solutions for Lipschitz nonlinear as well as bounded Jacobian systems. There's many other papers in which other types of nonlinear systems can also be similarly solved for. We looked at MATLAB code for doing LMI solvers for observer problems. And then finally, we looked at how a nonlinear observer could be applied to automotive slip angle estimation, in which there were nonlinearities in both the process dynamics as well as in the measurement equations. And so we saw that good performance with experimental data could be obtained even in the presence of saturation in tire forces for this application. So that concludes my talk. So for more information, please look at some of these papers published by various authors that you can find, and they contain more information on not only the results that I talked about here, but also extensions to other types of nonlinear functions. That concludes my talk. I'm happy to take questions if there's a way to do that. Okay. Yeah, please go ahead. Yes, I'm able to read your text. So yeah, if you type your question, I can read it out. Okay. I see a question about, can these LMIs be solved in real time for the slip angle problem? So let me answer that question first. So we don't need to solve these LMIs in real time, because what you need to do is you need to find a solution to the LMI offline, and typically in many of these applications, the L is a constant observer gain matrix. And so once you find L, you can use that L in your observer, and you don't need to keep solving the LMI in real time. You just solve it once, and you know, that would be adequate. There might be some applications where you know, you might for various reasons you might need to solve the LMI in real time, but certainly for the slip angle estimation problem, there was really no need to solve solve for the L in real time. So that is one of the advantages of these LMI type of solutions for nonlinear observer design. especially if you compare it to EKF or the UKF. You don't need to keep solving for the observer gain. You essentially try to get one constant observer gain, and that observer gain can give you global stability. So the EKF, for example, would give you local stability, and you would keep solving for the observer gain. But here, you would get global stability with constant observer gain. I'm sorry, I saw a question pop up briefly and then it disappeared here. I have to find a better way to be able to see the question. I saw something about an aerodynamic force and then it kind of disappeared on me. Okay, I don't see the question, but I click on the chat button. Okay. Okay, I see that now. How can an aerodynamic force be estimated using a nonlinear observer? Yeah, so if you have a term such as x dot square for aerodynamic force, or x dot square times signum of x dot, then you can design, you can basically, one way to do that is, you know, if you know that x dot is bounded, then you can have local bounds on the Jacobian of the nonlinearity. So even though x dot square by itself is obviously not globally Lipschitz, but if you assume that x dot is bounded, that the speed of the vehicle is bounded, then you can design the observer to be stable for a certain region of attraction. So it might not be globally stable, but it will be stable for a predefined region of attraction. Okay, so the question is, for the vehicle slip estimation, did you do any comparison between the nonlinear observer and a linear observer? How much better is a nonlinear observer? So I think we saw in one of the data plots that I showed you, we saw that the system clearly exhibited nonlinear behavior, meaning there was saturation in tire forces with slip angle. So of course you could do linearization and, for example, use an EKF. We haven't really, for this specific application, we haven't done a you know, extensive comparison between a linear observer and a nonlinear observer, but for some other applications we have. So for example, we have worked on a magnetic position estimation problem where we have compared an EKF with a nonlinear observer, and in this specific application, the output nonlinearity is basically non-monotonic, and so the points where the slope of the output function, so the points where the slope changes from being positive to negative, that point changes because of uncertainty in the model. And in that case, we've shown that a nonlinear observer works significantly better than EKF for that application. So is there any good way to find bounds for terms for ground vehicle dynamics cases? Yeah, I think so. So in the case of ground vehicle systems, you often have the velocity is bounded, and even if the nonlinearities happen to be non-Lipschitz, you can find local bounds on the Jacobian of the nonlinearity, and that's certainly possible. There's a number of vehicle-related applications that we have worked on. I would be happy to send you examples of different vehicle-related applications, in which people have used nonlinear observers. Okay, and then I saw this question here. Is there any way to analyze the transient behavior of the observer? So adding a convergence rate to the observer, which is one of the things we talked about on these slides. So that will give you a minimum convergence rate, and so that is one of the things you can use to influence the transient behavior of the observer. Some other tools that you can use, you can also bound the size of the observer gain, so there is additional constraints you can add on how big the observer gain is allowed to be, so that can be made a part of the LMIs as well. So there's some other question about functional observers. So this is not something that I've worked on, but I can send you some references on those. So there is some question about the condition number and LMI constraints, and is there a relationship between the performance of the observer and the condition number? So in general, in making the condition number of the eigenvector matrix, by achieving a good condition number, you make the system more robust. So the initial slides that I presented about the design condition involving the condition number and the locations of the eigenvalues, so we don't have good numerical methods for ensuring that that type of condition number constraint is satisfied, and therefore we moved on to using LMIs for doing the observer design. Okay, now I see a question about noisy plant model and H-infinity disturbance rejection, and the question is, in this case, is the error converging to 0 or a bound around 0? The answer is it converges to a bound around 0, right? It won't, so if you have an unknown disturbance, in the absence of the disturbance, the observer is guaranteed to converge to 0, but in the presence of the disturbance, what you're doing is you're satisfying an H-infinity type of constraint, And so what you can do is you can make the ratio between the norms of the estimation error to the disturbance. You can make that ratio small. So you can do disturbance rejection, but you cannot make the error zero in the presence of a disturbance. Okay, continuous and discrete time systems. I mean, there are different papers on discrete time observer design that have been published as well. So oftentimes, the original equations of a system are continuous time equations, and sometimes they are discretized for various reasons. If you have a processor with good with high sampling frequency, then I think it's fine to design the observer in the continuous time domain and to implement it in the discrete time domain. But still, if you use a high sampling frequency, you can certainly hope that your stability conditions which were guaranteed by your observer in the continuous time domain also hold in the discrete time implementation. But there are also several papers on discrete time systems as well. If you really want, you can contact me by email and I can send you some references for those. Okay, so there is some question about the unknown friction term, and so one way to address that situation would be to treat the friction coefficient or a variation from a nominal value of the friction coefficient as a disturbance. The other way to do it would be to estimate the friction coefficient by using the longitudinal vehicle dynamics and then use the known value of the friction coefficient in the slip angle estimation problem. Okay, so if there are no other questions, should we end the presentation here? Thank you, Tansel. Thank you all.